Hey there everyone, welcome back. So this example, we're going to be using both Pascal's principle and Archimedes' principle in trying to find a couple things about this submerged cube underwater. All right. The first thing we want to try and find is the total downward force on the top of this cube, right? Well, we'll need to use Pascal's principle for this, okay? Part B, we want to find the total buoyant force upwards on this cube. Remembering that's really the difference between the force down and the force up, right? And lastly, we want to find the tension in that connecting string, okay? So before I start, I should differentiate between two types of pressure, right? Because part A we'll see what the two types of pressure are. The two types are absolute pressure versus what's known as gauge pressure. Okay, what's the difference? Well, absolute pressure is measured from, well, a pressure of 0, right? It is the absolute pressure that you could get, right? So in other words, where is there a pressure of 0? Where is there an atmospheric pressure of 0? Well, when you're above the atmosphere, right? In other words, outer space. So atmospheric pressure is measured from space, basically, at the top of the atmosphere. Gauge pressure is measured from sea level. In other words, where the atmospheric pressure is 1 atmosphere. Okay? And by the way, this 1 atmosphere is also defined as 100,000 pascals. Okay? So keep that in mind, right? Two types of pressure. Absolute, measured from a pressure of 0. Gauge pressure is always measured from, well, the atmospheric pressure. Think of a bike tire, right? A tire gauge. That's measuring the gauge pressure. Because if you, say, open up the gauge, well, that's measuring the pressure of the atmosphere, right? And if you put it on your tire, then the pressure increases by an amount of the pressure in the tire, okay? So we'll take a look at both of these types of pressures in part A. So for part A, the total force on the top of this face right here, which has an area of L squared, by the way, it's submerged under the surface by a distance L over 2. Okay? Well, contributing to this force is not only the weight of the water, right, above this height, or above this depth, if you will, but it's also the weight of the air molecules above the water, right? It's all of those acting together to collectively provide a weight on the top of this surface, okay, pushing down. So let's find the absolute pressure, right, and the absolute force. So let's see. In order to find the force on the top, which is defined as the pressure at the top times the area of the top face of the cube, we need to find the pressure at the top. And by top, I mean right there. Okay, well, that pressure is, well, the pressure of the atmosphere plus an increase in pressure because we're going down in the water. And thinking back to Pascal, that pressure is rho g times whatever depth we're moving down. So this turns out to be, using SI units now, 100,000 pascals plus density of water, which I said was 1030, times g times the depth, which was L over 2, and L was 0.6. So this gives us 0.3. Right? And so here we have roughly, what did I have here? 103,031. Units are pascals. Okay? So this is a pressure on the top surface. If we wanted to find the gauge pressure, actually I should say this is the absolute pressure. Okay? The gauge pressure is then Well, this number minus 100,000, right? So the gauge pressure is just 3,031. That's the pressure here, as measured from the atmosphere. That's the gauge pressure. Okay. Anyway, we're using the absolute pressure for this problem. So now that we have the pressure, we can multiply that by the area and finally get the force on the top of the cube. So 103,031 pascals times 0.6 squared. And this should give us, what do I have? About 37,000 newtons. That's the magnitude of the force pushing down on the top face. Okay, so now for part B, we want to find the total buoyant force, which, remember, is kind of the sum, in fact, it is the sum, of the force pushing down on the top with the force pushing up on the bottom. All right, the bottom one will be bigger, and the difference is the buoyant force, which always points upwards. So really, you can write it out like this. Bottom minus the top. All right? And so to find the force on the bottom, well, guess what? We do the exact same thing we did in part A. Okay? So let's see. To find pressure at the bottom, let's write that out here. It's the atmospheric pressure plus rho g h, but that's the h for the bottom, which should give us 100,000 plus the density of the water. Oops, I'm not going to have room. Plus, or times 9.81 times this h for the bottom is L over 2 plus another L. So that's 1.5 L. 3 halves times 0.6. And now this should give us a pressure at the bottom of 106,062. I'm just going to make another line here. So we take this pressure now and multiply it by the area. It should be the same as in part A. So 106.62 times 0.6 squared. All right, the area for the bottom face, L squared. And then we subtract what we got in part A, basically, right? Which was 3.7 times 10 to the 4. Whoops, I'm leaving all off units, okay. And so now the buoyant force, being the difference of those, should be about 1,100, right? I get 1091 newtons. And again, that's directed upwards. Okay? And now for part B, for part C, we can use the fact that we have the buoyant force, the object's weight, which I should write this in vector form right there. We have FB, we have its weight, mg, and also we have the tension, T. So for the net force equation, we have the tension's positive, the buoyant force is positive, but the box's weight is negative, and all that's equaling 0. And we want to find the tension. Well, let's see. mg minus the buoyant force. Do we have the mass of this block? I hope so. Yes, 450 kilograms. Okay, so plugging in those values, we should get a tension of approximately 3,300 newtons. for the tension. All right, so this was how we kind of used Pascal's principle to estimate the pressures and the forces at various depths, as well as the buoyant force to find the difference between the force on the top and the force on the bottom, right? We're still using principles from chapter 5, but just in terms of fluids. All right, thanks for watching.